Welcome back. In this class, we continue a little bit more about NMR instrument. We already discussed quite a bit in the last class, especially with a more focus on superconducting magnet and shim coils, etc. And I wanted to discuss probe in this class. Before that, I wanted to tell you, I didn't discuss about the type of materials that we use in superconducting magnets. Generally, the superconducting magnets consist of superconducting wires made up of thin wires made up of superconducting materials, which is niobium titanium, niobium iron alloy, which is thin wire. The length of this superconducting material, that wire, runs up to several hundreds of kilometers, wound in the form of a coil, and then inserted in the liquid helium to attain magnetic field. And then when you charge the magnet, there are charging leads which are inserted, and then steadily we keep on passing the current through the coil. Slowly we keep raising the magnetic field. When the electronics matches with the magnetic field, when you start detecting the signal of NMR, we know we have got the magnetic field, generated the magnetic field. Then join both the other ends of superconducting material and leave it like that, making the current flow forever. But the general thing about superconducting magnets. And I also told you about shim currents, which are essential to get the homogeneity perfectly. Today, let us see what is a probe. This is a very quick introduction to probe and other parts. What is a probe? The probe is another important component of a spectrometer. This is where you transmit RF pulses. Pulses are generated RF frequency by a transmitter. Finally, there is a coil inside the probe, RF coil, that acts both as a transmitter and also as a receiver. That's very important component is probe. You may do everything. If you have no probe, you cannot detect the signal. You cannot exit the nuclear spins. The probe is another important component of a spectrometer. The probe is like this. See, inside we have simply a coil here. When you put the sample here, the sample the tube goes and sits inside this RF coil. Okay, the sample sits here. Now, when we are through the transmitter to the console, you generate the radio frequency pulse, and pulse, and you send the pulse. This coil is the one which ensures the spins inside this NMR tube get excited. Afterwards, the free induction decay which is induced is into this coil only. This acts as a receiver coil, both as a transmitter and as a receiver coil. And then signal is collected and fed to the spectrometer, of course amplified, pre-amplified, fed to the spectrometer for processing, like Fourier transformation, etc. But basically, the probe is the one which has RF coil, which does the job of transmitting and receiving the signal. And a small coil, okay. Most probes contain two coils. Okay, you may ask me why two coils? Of course, one single coil does the job of both excitation and detection. Only single coil. That will do for NMR. It will send the RF pulse, detect the signal also. But there is another type of coil, another coil will be there, which is also kept, that is for tuning to the deuterium frequency of the spectrometer. That's why different probes are designed for a different spectrometer. You cannot take a probe for 300 megahertz and start putting it into 800 megahertz spectrometer and record the spectrum. It is not possible, because the coil is tuned for a particular frequency. This is for a deuterium clock, deuterium frequency. Okay, you can tune it. Okay, and then beyond a certain thing, of course, there is a problem. You cannot have this for all the frequencies. The one coil is for deuterium lock, other is tuned for other frequencies, and the deuterium lock is used for preventing the field drift. This is called a field frequency lock for which we use this. And one more important thing is, when you send a radio frequency pulse, that is the input RF frequency, at the probe frequency, let us say I am detecting carbon. I am going to send a radio frequency at the carbon frequency. And the probe should also, this coil, I have to tune this frequency to match for that. So that matching of the frequency, so that it can emit only that particular frequency. It can exit the spins at that carbon frequency. In addition to tuning, this is matching of the frequency of the detection and the RF, which is probe frequency, and the input RF is called matching. At the same time, this transmitter, these coils will also have what is called an impedance. Impedance is something which you need to understand. Of course, it's a basic, simple electricals. You would have studied that in your high school or even PUC. What is a impedance, what is a resistance, and what is inductance, everything you would have understood. Okay. Now, in the impedance of the transmitter and the receiver has to be matched. They should perfectly agree. If there is no impedance matching, then what is going to happen is all this power you apply through radio frequency pulse through this coil will not go to the sample. Some of them get reflected. It is called reflected power. So the matching is an important thing. Matching of the impedance of the transmitter and the receiver, matching of the input radio frequency with that of the probe frequency is very important thing in the probe part. This is called probe tuning and matching. Both are done. As soon as you put the sample, or when you want to do a particular resonant frequency, you want to see of a particular nuclei, first thing is you have to tune the frequency of the probe so that you can transmit signal for that frequency and receive signal. And also you have to ensure that the impedance of this transmitter and receiver is matched so that maximum power what you put in, you go to that, there is no, that minimum reflected power is there. That is called matching. So it is basically this is a probe circuit. It is nothing but a simple LC circuit. There are two capacitors, tuning capacitors for matching the, and tuning capacitor is to tune for the right frequency, and matching capacitor is to match the impedance. Okay. And how do you match the impedance? There are two types of impedance matching, which you know in basic electricals. One is 50 ohms matching or 70 ohms impedance matching. I think most of the spectrometers use 50 ohms impedance matching. So this capacitor is tuned to match the transmitter and receiver impedance. This is tuned to match the input frequency and the probe frequency for the nuclei of our interest. And this is the sample is put. This is RF coil. Very simple, right? Very simple circuit. Simple R circuit here. Now, coil and the two capacitors forms a resonant circuit. It is like a simple LC circuit, I said. It has a capacitance and the inductance. Once you have the capacitance and inductance, you know what is the frequency. The frequency is given by 1 over root of L into C. What is L? L is inductance. C is the capacitance. If you know these two, you know what is the frequency for which you have tuned. That is why I said changing capacitance is there, Here, you have two capacitors, tuning capacitors. When you tune the capacitors, you are varying the capacitance to match the frequency and also to match the impedance. Okay. So inductance of the coil is approximately sum of the capacitance C1 and T2 here. Sum of this capacitance of these two. That is the inductance. And that will determine the resonance frequency. Nowadays you may have a probe. Varieties of probes are there. Multinuclear probes. One probe you can tune to varieties of frequencies over the wide range of frequency. You can study in the same probe carbon, all other different nuclei up to carbon, silicon, nitrogen, aluminum, any nuclei of your interest. All you have to do is to tune the frequency, vary the capacitance, and see that the probe frequency matches with the input frequency. Now you can detect that nuclei. So that is what is done in the present day spectrometer. We have broadband tuning probes are available. So totally, please remember, Inductance of the coil is nothing but the sum of the capacitance approximately. And when you tune it to the right frequency, it is called tuning of the probe. And matching is nothing but, I said, matching of the impedance. Why it happens, why you have to match, is for this reason. The radio frequency waves cannot be efficiently transferred over regular wires. Like you connect electrical wire in your this thing. You cannot connect like that for a radio frequency. It is not possible. So there are what are called transmission losses. This transmission loss is because of these cables have characteristic impedance. These transmission lines. So you cannot transmit through a regular wire. They are called RF cables, radio frequency cables only. You have to pass RF frequency only through that. And because of their characteristic impedance, you have to match it so that the transmission line and the load at the other end, at the probe end, should have the same impedance so that there is no mismatch in the frequency. So impedance, if there is difference, there is a mismatch condition, and we get what is called the reflected power reflection, or sometimes it is called standing waves. What it means is, as I told you earlier, if there is a mismatch of the impedance, all the RF power that you have putting to generate the exact 90-degree pulse, you would have calibrated and got the 90-degree pulse. But all RF power is not going into the thing. It is not efficiently transferred. It leads to loss of signal. So matching is an important condition. Okay. And remember, I said it appears because we have to use transmission lines, radio frequency transmission line, not regular wires. As a consequence of their characteristic impedance, this we have to do to minimize the reflection or a standing wave. The matching capacitance provides transforms high impedance. And then what it does is transform high impedance of a parallel resonant to low impedance, that is 50 ohms. And this input, this you have to match for the input of the receiver. That's why I said impedance matching is 50 ohms. Okay, please understand. The matching capacitor, which I showed in the spectrum, simple LC circuit, provides transformation of high impedance in a parallel resonant circuit to low impedance. That has to be matched for the impedance of the receiver. That's so that we both will maintain 50 ohms. That is matching. Another advantage of matching of the probe, if I don't match properly, what happens? The shortest possible line will be there if you match it. Because you are putting full power, entire power goes to the sample. Otherwise, you think you are applying some power, majority of the power comes back as standing waves or reflection, then sample will not feel full power. So, for a 90-degree pulse width of 5 microseconds, let us say you need to have only 30 or 40 watts of power. You may have to use more. You may have to use double it because the entire power is not going inside. So, that is a disadvantage. So, that's why if it is matching, you can get shortest possible pulse width. Advantage of it, you have a uniform excitation over a wide spectral bandwidth. That's what I said, when I was explaining the RF pulse. For a uniform excitation of a wide bandwidth, you need pulse width which is short pulse width. That's very good. So that is possible with a perfect matching. So when the signal, when you have a perfect 90-degree pulse, perfect excitation, your signal to noise ratio will go up. You get full signal you are going to detect. That's also important. Supposing in an experiment like carbon-13 you are detecting, what you will do? You will do the proton decoupling. If you use the decoupling, you have to remove the coupling between protons and carbons. Then you are applying much more power, about 100 to 200 watts of power you apply. Okay, such a large power when you are applying, you have to ensure that entire power goes to the sample. Otherwise, it is going to cause problems. There won't be efficient decoupling. So, if perfect matching of the probe impedance with the input, or if it is done, then what is going to happen is you have a efficiency decoupling. So, the matching and this thing is very important. Remember, output impedance of the transmitter and input impedance of the receiver should be perfectly matched. And you got efficient pulse width, very good signal to noise ratio, and efficient decoupling. And just to tell you about the type of coils we use in NMR, normally we use this type of coil, Helmholtz type coils. And of course, different applications in NMR have different types of coil. Sometimes we use saddle coil, sometimes we use solenoidal coils, like sometimes we use Helmholtz coil. And in, of course, extension of the RF is MRI. If you go, they can use bird cage coil, like a cage where a bird is put. It is called a bird cage coil. Okay. So all these things, different types of coils are there. And based on that, based on the type of probe, you can find out what your coil is. Generally, we use Helmholtz coil, what is normally used. Okay. And if you go to the solid state NMR probes, where you use a solenoidal type of coils. And then afterwards, the coil, what it does is, you send an 90 degree pulse, excite the spins, collect the magnetization. And you know, the EMF induced is very, very small. I told you, less than microvolts, sometimes nanovolts, several hundreds of nanovolts. We have to amplify that. That is done by pre-amplifier to the range of 0 to 10 volts, it will amplify. And then fed to the computer for all other processing. Okay. And if I just to give you the picture of the different types of probes available, we have broadband. This is from our lab what we have. Okay, we have a broadband inverse probe. We have a TXI probe. We also have what is called a cryo probe, and 1.3 mm probe also we have like that. We have 1.3 mm. We have 0.7 mm probe, not 0.7 mm. I think 1.3 mm probe for solid state also. So this cryo probe is another thing which is the technology which has evolved over last decade, a decade and a half. It's very important is the cryo probe. Here, the instrument also has a thermal noise. Okay, a coil will be, when you are detecting the signal, noise also will be picked up, thermal noise. So what it does is, to prevent the thermal noise, we have a cryo probe where most of the coils and the electron is kept at the cryo temperature, so that thermal noise, everything will be reduced, and you have better signal to noise ratio. Only you pick up the signals more. And this type of probes gives better signal to noise ratio, at least 3 to 4 times more than the conventional probe. In theoretically, it should be 4 times more than a conventional room temperature probe. So cryo probes are very advantageous, but remember, very, very expensive. A cryo probe for a particular spectrometer, let's say 700 or 800 megahertz, will be almost the cost of a spectrometer itself, or almost 2/3 the cost of a spectrometer. Or with this cost of a cryo probe, you can buy a low frequency NMR spectrometer of 300 megahertz or 400 megahertz. Complete set you can purchase. That is a very expensive thing, but it has a lot of advantages. But that's why, because a lot of technology, a lot of research has gone in to design such a probe, so it is very expensive one. What I'm trying to say is, there are varieties of probes available, and you can get a custom-made probes of your choice. You can have a dosy probe for this thing. You can have a fluorine probe, only dedicated for a particular nuclei, like only proton probe. Varieties of things you can do. The vendors are nowadays able to give you types of probes which can do all these sorts of jobs that you require. Whatever the type of experiment you want to do, you can do. Okay. Now, the special features of FT-NMR spectrometers, we have a single coil, large power, and very small signal voltage and precise sample. So as a consequence, so we can apply the transmitter for a small microsecond and receive the signal for few seconds. As I said, FID dies for few seconds. Free induction decay is of the order of 2 to 3 seconds. So this is special feature of FT-NMR spectrometer. Also, we have what is called analog to digital converter. I said signal is analog, but it is collected in a digitized fashion. So analog signal will be digitized like this. This is analog signal. It will be digitized like this and collected. And ADC is very important. The largest number of ADC is defined by the number of binary bits that ADC uses. For example, if you have a 3-bit ADC, you can have like this. 32 bits is commonly used in NMR nowadays. The ADC is very useful because you have to digitize the data at regular intervals. If the ADC is Smaller ADC you have lower resolution. You can't digitize with more number of data points here. So higher the size of the bit size of the ADC, better is the spectrum. Okay. So this is a typical example from taken from Keeler's book. You can see for a 3-bit ADC, this how the signal is digitized. So then you may ask me a question: what is the maximum bit size available? If the bit size is an important thing, why can't we have infinite bits? There is a limitation. Technologically, everything is not possible to achieve infinitely. Okay, there is a technological limitations for everything. So the commonly presently used is 32 bits. Sometimes 32 bits, in case you can go a little higher. Okay. How does ADC work? It's a very simple way. ADC converts signal to analog signal, digitizes and puts into zeros and ones. That's a digit, binary digits. 0 and 1 are binary digits. ADC does electronically convert the signal to zeros and ones. And it samples at regular intervals and assigns an intensity value for each of the points. Okay. It takes the signal, samples the signal at regular intervals, and for each of this, it assigns an intensity value, and this value cannot be anything. For example, intensity from a 4-bit ADC, if you take here, what is it? Okay, here I have taken 3-bit ADC. It should be 3-bit. Okay, we'll take the 3-bit ADC. How do you represent a 3-bit ADC? Of course, if you know digital electronics, you know. 1 is 0, 0, 0 is 0. This is 1. If the number comes here, it is 2. If it is 1 and 1 here, it is 3. If the number 1 is here, it is 4. You know that how to generate 1 to 7 or 1 to 8. So this is in the 1, 2, 3, 4, 5, 6, 7, 8. So if you take a 3-bit ADC, there are 8 possible intensity values you can have. 1, it can be 0, it can be 1, it can be 2, 3, 4, up to maximum of 7. That is the intensity values it can give. And when it collects the signal, smallest signal will be given this intensity, smallest value. And the highest signal will be given the highest value. Just to give you an idea, you take a sample with a huge, strong peak. For example, in a water-soluble sample, residual water peak is very strong. Huge peak will be there. And if your sample peaks are very weak in intensity, they will be assigned low values. Whereas water peak will be assigned highest intensity, okay, of this 37. So that means that digit is full, that bit is full, how highest intensity is assigned. This is how when you sample, intensities are assigned for smaller and larger values. And the smallest signal will be for this 2 to the power of 0 is 1, and highest intensity value is, I'm sorry, not 2, it is 2 cube. I made 2-3 mistakes in the slides. It is 2 cube, it is equal to 8. Remember, it is 2 cube is equal to 8. And it is not 8, it is 2 cube. Okay, this one equal to 8. So highest ADC, higher ADC gives better resolution. This you will see the advantage of digitization with higher ADC. Comparison of the spectrum with a 6-bit ADC. You have 64 levels. 2 to the power of 6 you calculate, find out. This is 8-bit ADC. You have 256 levels. Like 3-bit we had 8 levels, 0, 0, 0 to 1, 1, 1, right? Here we can have 6-bit 64 levels and 8-bit 256 levels. So you can have a better representation of the signal, and higher the level for representation, better representation of the signal. You can see much better than the 6-bit ADC. This is a very important point. And of course, this ADC resolution also is important for spectral resolution. I told you, the spectral width, once I gave the expression 1 over 2 times delta t, which is nothing but 2 times the dwell time. So the dwell time has to become such a smaller and smaller, so that you can digitize with more number of points. Remember Nyquist theorem, everything I discussed, where this is the dwell time. So higher the digitization points, is better for us. So higher bit ADC is always good to utilize. Okay. A typical ADC can have 16 to 32 bits normally. Of course, in NMR, we use 32 bits ADC. In some little older type spectrometers, couple of decades older, people are using 16-bit ADC. Now you can see that in a 16-bit ADC, what is the lowest intensity possible? 1, 0, 0, 0, 2 to the power of 0, 1. Highest intensity is 2 to the power of 16. Calculate what is 2 to the power of 16. It comes of this order. Okay. So that is 65. That's why I said when I was telling you about choosing the size of the data points, it always goes by, when you are choosing the number of data points, it always goes by 2 to the power of n. So it is 2 to the power of 16 you have to take. Similarly, if you say 2 to the power of 8, 2 to the power of 6, like that, 1K in this convention is 1024 data points, not 1000, because it has to be 2 to the power of n. Okay. So this is 16-bit ADC. You can have highest signal intensity of 65K. What it does is take the highest intensity of the signal, give that value this much, and for the lowest intensity gives this. Similarly, for a 32-bit ADC, highest value you see is too huge. See the difference. That is why now in this case, your spectrum is better represented, better resolved. And a fantastic way of representing is go to higher ADC. This is what it is. And then it will overcome the problem of what is called a dynamic range. What is a dynamic range problem in NMR? I will tell you soon. What happens is, when the largest value is in the time average FID, in the sense I keep on acquiring the signal by doing signal averaging. The largest value, when it overflows the computer memory, okay, it will keep storing in the different cells of the computer. When it overflows it, the data must be scaled to continue averaging. If let us say largest value is assigned to the maximum value, it is full, memory is full. It cannot take any more data. If you do signal averaging, nothing will help. What happens is, this signal keeps on increasing. And because this is highest intensity, it is occupying the maximum intensity, all small intensity peaks get suppressed. Why? Because when it's full, when the memory cell is full, then it divides each by a factor of 2. I have a big peak. Then it will divide by 2 to continue further. Then the small peak which was here, that also will be divided by 2. Already it is weak. Further dividing by 2 to fill the memory, you lose the intensity, lose the signal. Again keep acquiring. This fills faster. Now again it divides. This further goes down intensity. Signal intensity, because stronger signal fills the memory faster and keeps going up and up and up in intensity. Smaller peaks will not add up. In fact, after some time, the intensity will come down. It will not increase at all. Because every time memory is full, ADC is scaled by a factor of 2 to allow further accumulation of the data. That is called, this type of problem is called dynamic range problem. So in which case, a very strong signal, if it is there, you have a dynamic range problem. Weak peaks sometimes you will not be able to see, because the memory overflow cuts the signal, scales each of the signal by 2. As a consequence, weak signals also will get reduced. This is a dynamic range problem. Please understand, it is very important. Sometimes when you have a very strong signal, you may not see the signal from your sample. It is for this reason, because the ADC gets full. And when this is the thing, what happens when this process reaches a point, then what happens? ADC represents a larger value. No amount of additional time averaging can help. It can only, small signals will never be brought out of the noise. So these are some of the important points which I wanted to tell you as far as the NMR instrument is concerned. What technical details were there? It is a broad bird's eye view. You should have an idea of a spectrum, what an NMR spectrometer is, what a magnet is, what a quench is, how you fill helium, liquid nitrogen, you should go and see in the lab. What is a helium? Why you require a helium? why you require a nitrogen for the magnet. These are all some of the technical details, but nevertheless, you should have some idea. Okay, so I'll stop this. I've given you, as far the practical aspects of NMR is concerned, everything. Okay, so we will switch over to a different topics in the next class.